Alright, so now moving on to high dimensional data and feature selection. So we have dimensionality reduction and feature selection approaches. We have PCA, TSNE, and other low rank approximations. In PCA, and then we have feature selection approaches. We have filter methods, wrapper based, and embedded approach. So let us go through this in depth, right? So discuss the high dimensional data and feature selection, and finally we would have real world applications and uh, you know for AI and health policy, which we'll discuss in a bit. First, let's discuss. Medical data science frequently encounters datasets with a large number of variables, features, leading to computational and modeling difficulties. So, high dimensional data refers to datasets where the number of features significantly complicates analysis. An example is a data frame used in tuberculosis research that contains 136 observations with 425 metabolic variables. Intuition failure. A core challenge of high dimensional data is that it does not behave in a way that is consistent with most people's intuition. Consequences: in high dimensions, data points are always close to the boundary and further apart than one might think. This property makes it difficult for complex models to perform well, leading to the conclusion that only the simplest models would work well in high dimensions. So, to manage high dimensionality, data science utilizes techniques to create low dimensional representations while preserving essential information. So, these are referred to as low rank approximations. Like, first, we have the principal component analysis. So, PCA is a primary method for achieving low rank approximation and is used for both feature engineering and visualization. So, PCA linearly transforms the data to a new set of dimensions, principal components that capture the maximum variance in the data. Mechanism is it calculates a covariance matrix, which measures how different variables change together. Then apply an affine transformation to translate the data center to the origin and rotate it to diagonalize the covariance. Then using singular value decomposition (SVD), a matrix decomposition technique that yields a low rank approximation. Then basically the principal components are abstract representations of the original data. PCA can be used for feature engineering and feature selection. It has practical uses in domains like approximating faces and distinguishing biological classes. Then we have non-linear dimensionality reduction techniques. So for data that cannot be adequately reduced linearly, we can use TSNE, like T stochastic neighbor embedding. T stochastic neighbor embedding, which is a technique for non-linear dimensionality reduction. So TSNE calculates a similarity measure between pairs of instances in both the high dimensional and the low dimensional spaces, optimizing these measures using a cost function. So it is particularly useful for visualizing high dimensional data, as shown in the example for clustering MNIST digits. Then we have feature selection methods. So it aims to identify the most relevant subset of variables to improve model performance and interpretability, falling into three main machine learning categories. First is the filter method. So filter methods select features based on statistical characteristics, independent of the subsequent classification algorithm. So correlation based feature selection is CFS, a subtype that explicitly considers redundancy. The principle is that a good feature subset is one that contains features highly correlated with the class yet uncorrelated with each other. Mechanism is CFS uses optimization techniques like genetic algorithms or hill climbing search to achieve high merit scores. Then we have wrapper methods. So wrapper methods use the ML model itself as the evaluation criteria for feature subsets like forward or backward selection or on a RFE that is recursive feature elimination. And finally, we have embedded methods which perform feature selection as part of the model training process itself, examining training iterations to rank feature importance. So we have lasso regularization first, that is the least absolute shrinkage and selection operator. It adds a regularization term lambda proportional to the L1 norm of the coefficients. So lasso is basically a preferred method for feature selection among regularization techniques because of the L1 constraint that forces coefficients to become exactly zero at a certain lambda, effectively removing the corresponding feature from the model. And we also have ridge regression, which is using the L2 norm constraint and prevents the coefficients from becoming too large, but generally does not force coefficients to zero, making it less suitable for direct feature selection than lasso. Right. So also ridge regression is noted for performing better in explaining data if there is collinearity. Right. So we have covered all that. Now covering some applications, real world applications. So after that, that would cover our whole topic. So let us go through that. So basically, we have AI and explainable models for health policy, the longevity gap study. A major application highlighted is the use of explainable AI (XAI) models, specifically the Bayesian decision networks, to address complex socio-demographic challenge of the longevity gap in the United States. The core motivation for the work is to learn policy for mitigating the longevity gap using explainable AI and release it to public and policymakers. So the Bayesian decision network model drew on extensive data sources, including mortality, that is census, given by census, healthcare indices, Dartmouth Atlas, health behavior, CDC, BRFSS, socioeconomics, and demographics. The resulting inference yielded actionable, quantified policy message. Right. Social diversity basically mitigates health inequality in the US. Counties with higher diversity are 38% less likely to have a longevity gap between the rich and the poor. The likely it should be countries. The likely explanation derived from the network structure is that higher diversity is associated with higher income, especially in females, thus improving healthcare services. Then we have preventive care quality. Countries with high quality primary care services, including investigations, not just visits, show a 43% increase in probability of living beyond 85 years in females, with a corresponding 30% increase for males. The most impactful primary care investigation identified was annual lipid testing, especially in diabetic population, because diabetics are at the highest risk of cardiovascular mortality. Then we have the clinical income link, right? Clinical income link, acute mortality, that is 30-day hospital mortality index, is 30% less in countries with household income in the highest segment. Pneumonia was identified as the highest contributor to acute mortality in lower income households. Social demographic factors, right? These are also the sources that, as you can see, that I mentioned here. The network quantified the impact of traditional health factors and social stability. Countries with lower family stability are 40% more likely to have lower social mobility. Family stability decreases crime rate, increases upward social mobility across economic tiers, and indirectly decreases Gini disparity in countries. High life expectancy in males makes it 33% more likely for smoking to be in the lowest stratum in that country. These explainable AI models are designed to be deployed as web applications to aid policymakers, right? AI for public health and global policy. So, antimicrobial resistance (AMR). AI is used to study emerging trends in antimicrobial resistance in bloodstream infections across India via a multicentric longitudinal study. Research also focuses on estimating the impact of health systems factors on antimicrobial resistance in primary pathogens. Then we have the SDGs, that are Sustainable Development Goals. That evidence-based policymaking must leverage AI for tracking progress on global goals like Sustainable Development Goals. And public awareness like ML has been applied for raising WASH awareness during COVID-19 pandemic. Finally, we have FHIR, which is the technical foundation supporting the exchange of data necessary for modern computing and medicine, and is increasingly mandated by regulators for policy adherence. Smart on FHIR and EHR integration, which is a framework that allows third-party apps to connect securely to EHRs, systems like Epic, Cerner, or Allscripts in a standardized, interoperable way, and defines the authorization and app launch layer on top of FHIR using OAuth 2.0 and OpenID Connect. Then we have the US regulatory policy. So, US regulatory efforts are leveraging FHIR APIs to enforce policy changes. The CMS interoperability and prior authorization rule uh, builds upon FHIR APIs for payer provider data exchange. This reform accelerates patient care by requiring affected payers to issue prior authorization decisions within 72 hours for urgent requests. Then we have global health systems, FHIR being implemented globally in national health infrastructure. India's FHIR stack ABDM uses FHIR for discovery of patient information and includes a health ID and consent management framework. The UK is building PHRs, personal health records on FHIR, right? So adding a patient storing in database, you can go through that. Advanced analytics and AI capabilities. FHIR servers support advanced functions necessary for AI and policy analysis, including data analytics based on artificial intelligence, bulk access to data, and the ability to integrate determinants of health data. FHIR is also being leveraged for agentic AI applications, right? Then early success in health system improvement, Project Esther. An early example of targeted intervention leading to measurable policy relevant results is Project Esther. Though not explicitly using AI, this project demonstrates how focused design and implementation, likely based on early modeling or storyboarding, achieved significant improvements in healthcare delivery. Hospital admissions fell 22% from 9,300 in 1998 to 7,300 in 2003. Hospital days for heart failure patients fell 28% from 3,500 in 1998 to 2,500 in 2000. Waiting times for referral appointments with neurologists fell 84% from 85 days to 14 days, and for gastroenterologists fell 71% from 48 days to 14 days.